Good day, everybody, and welcome to this first lecture on derivatives. So, part one. This is the central concept of calculus, and today we'll actually introduce the concept and show a couple of examples on how this actually gets to work for us in this course. So, to begin, let us consider the graph of, okay, here's what I want to do. I want to sketch here three sets of axes. Here's an X, here's a Y. I want to redo that over here again. And I want a third one over there. So they're all exactly the same. And then what I'm going to do, I am going to basically come up with some sort of a function that I want to sketch here. Maybe, why don't we go with something simple, a parabola that is oriented upwards. So I'll do the exact same thing here. I'll try to reproduce the exact same shape of the exact same curve. So these are supposed to be exactly the same. And now I am going to put, I'll use green. I am going to put here a point X exactly at the same position on all of my three sets of axes. Okay, so remember in blue is the curve y equals f of x for all three of them. So what happens basically when I go to the curve and I have that point on the curve? What would be the coordinates of this point? Wouldn't it be something like, x and f of x, right? For this very point right here. What is that color? A mix of orange and green. What is orange and green? Halloween color? I don't know. And let's do the same thing here. So on the other graph, again, x to this point, and I have here, again, x f of x, and this time, x f of x, and here too, x f of x, here, x f of x. So this is just the same point on the graph everywhere. Okay, dokie. So, what is it that we want to do with this? Here's what we would like to do with this. We'd like to take another point further away. Let's have this point here further away. And let's call the distance between this point x and the point further away, let's call this h. So if the distance between x and the other point here is h, what would be the coordinate of that point? How would you actually call that point? This is x, and then I move h units to the right, so what would that guy be? Doesn't it have to be x plus h? Logical, right? So we'll do the same thing here, but we're going to use another h but smaller than this. So let this h be here. So this is h. And the same reasoning actually applies to this guy. This guy shall be also x plus h. I want you to notice one thing. If I put a ruler to this and I measure this h, I may get maybe like, I don't know, 4 centimeters, right? Roughly speaking. I don't know, didn't measure it. But what's actually important for the concept of derivatives is this. In the second graph, the h has gone from 4 to a much smaller, maybe 1 centimeter, right? I'm simply taking a smaller value of h, and you can probably anticipate what I'm going to do with the third graph. I'm going to have an h very, very, very close to my x. This time, oh boy, look at that little h here. This is h very, very small. If this was 1 centimeter, maybe this is 0.5 centimeter. So I'm shrinking the distance between those 2 points, between x and x plus h, x and x plus h, x and x plus h. Okay, so as usual, this point now is x plus h. I'm sorry if it's so small, but it's always the same thing. It's always x plus h. Okay, now what I want to do with this is take that, go back to the first graph. Let's take that point x plus h and let's go connect that to the graph. I need to extend this a little bit here so that they connect right here on the e of derivative. Okay? And then what I would like to do is connect the points. I would like to actually draw a line that connects the points together. So the line that will connect the points together is going to look like this a little bit. While this point right here on the graph, this very, very point right here, what are its coordinates? If I wanted to say this is a point of something. So basically, this point, its x coordinate is x plus h. What happened to you? There you go. Is x plus h. What is its y coordinate? What is the y coordinate of that point? Well, remember the curve, the blue curve is y equals f of x. So what happens if I put in x plus h? I'm going to get, of course, f of x plus h. Right? So maybe I make this a little bigger. X plus h, comma, f of x plus h. So I have this point, x f of x, and I have this other point further away, x plus h, comma, f of x plus h. Good. So I will be interested now in finding, well, something pretty natural about this line. What is the first thing that we can actually find when we have a line? It's slope, right? So what is the slope? Let's call it A. A for the slope. If you're used to M in high school, you can call it M as well. I'll just use A. It seems to be more universal. So what is A? Well, the definition of the slope that we saw in the 10th review video on analytic geometry. It is delta y over the delta x, right? And we know this is y2 minus y1 over x2 minus x1. So it's the difference in the y's over the difference in the x's. What is the difference in the y's? What is the y here and what is the y there? The y here is f of x plus h. And the other y right here is f of x over the difference in the x's. This is x plus h minus x. This is x plus h minus x. Little cancellation here. F of x plus h minus f of x. The cancellation happens in the denominator right here. X minus x, gone. And that gives me an expression for the slope of the black line. Okay, good. Let's separate this and let's redo more or less the similar analysis for the second graph. The only difference between the two is that here h is much larger than h here, like about 4 centimeters, and here barely 1 centimeter. But I am really going to perform the same analysis. That is, I'm going to take my new point, x plus h. I'm going to take it to the graph. And I'm going to figure out its coordinates. What are the coordinates of this new point? Well, the x coordinates is x plus h. The y coordinate, well, remember, this is still the graph of y equal to f of x, right? It's still the same function. So if you want to know what the y value is here when we have that point x plus h, you put it in f. And of course you're going to get f of x plus h, right? So, knowing this, I am going to draw a line that joins these two guys. Going to be a line like this. Notice that the difference between this straight line and that one is really the inclination. This one is actually steeper, and this one is a little bit flatter, right? And a measure of the inclination of a line, there's another name for that. How do you measure the inclination of a line? The slope, precisely. So we're going to find the slope of that again. Mind you, the formula has not changed since 5 minutes ago, so it's delta y over delta x. So the difference of the y's, here's a y here, here's a y there. So fx plus h minus fx over the difference of the x's. Here's an x here, here's an x there. So x plus h, again, minus x. No change from the one before, same formula. So this is f of x plus h minus f of x divided by x minus x goes away, and I'm left with this. Same formula, exactly the same thing. No big surprise, we're calculating the slope of a line and the points are the same. The only difference is the actual measurement of the h value, from large to small to smaller. All right, one last. Over here, okay, same analysis. I'm going to go to the graph with this new point, x plus h, which is very, very, very close. You see me coming here, huh? I'm thinking about an h being closer and closer and closer to a value. Closer and closer, what concept is going to be involved here? We saw that in the previous chapter. There's a limit coming. But for now, here's the point right here, very, very close to the original x. It has, of course, the same coordinates as before. It has x plus h, comma, f of x plus h. This point right here, right? That's its coordinate. I'm going to draw a line that's going to go right through these 2 points. It's going to look like this. Right? And maybe this is yet again a little flatter than that. And I'm going to calculate its slope. Oh well, that's getting to be pretty boring, pretty repetitive. Why? Because it's the same thing. Difference of the y's, difference of the y's over difference of the x's, x plus h minus x. Which, of course, is the same cancellation as before. It's the same formula, nothing changes. Very repetitive. Bon, what do these things have in common? They are all called secant lines, from the Latin secare, which means to cut. These are lines that actually cut the graph in 2 different points, here and here, here and here, here and here. Now, what I would like to do here is actually, I'd like us to ponder on what's going to happen when this h, which is already very small, 0.5 centimeters, when this h is actually made even smaller. What would happen if I actually shrank this h to 0.1, 0.01, 0.001? I would actually get something that would look like this. Those 2 points, they would be so close to one another, then they would actually become indistinguishable. It would be very difficult to tell them apart. What would I get, actually? Well, I don't have enough room to do it here, so I will erase this. But please keep that in mind, because right now, this is the last graph that I'm going to use for the continuation of this presentation. So erasing all this beautiful, colorful stuff in 2, 1, 0. All right. So, you know what? Why don't I redo here the last graph that we had, the one with the very small h, the one where the h is equal to 0.5, okay? We'll take 3 seconds. So we have this graph of f of x, same as before, no change, so y is equal to f of x. Yep. And then we have the x that is here, right? And the x plus h that is very, very close to it. So x and x plus h giving me this straight line right here. So this is x plus h, here's 1 point, here's another point, and we draw the line that goes through this, the secant line, yep, where this point right here, how do I do this? This point right here is what? Is x f of x. And this point right here, what is that point? What is that point right here? It is x plus h, comma, f of x plus h. Yuck. Like that. And the slope of this line, of this black line, the slope, has been found to be x plus h minus f of x over h. Okay, good. So we have the last graph from the previous whiteboard. Now what happens, when h is made to be even smaller? When h is made to be even smaller. By even smaller, I mean almost 0. Well, take a look at that. Here's the same graph. Here's the same set of axes. So we have here the same f of x. And now we are going to have an x here. And now the h is so small. So remember, like now here, h is not even 0.5, not even 0.1, not even 0.01. It's extremely, extremely small. So extremely small h. So it's like, the x and the h are so close to one another that you cannot tell them apart. In other words, this point on the graph is at the same time x and f of x, and almost also x plus h, comma, f of x plus h. So when I draw the line, I actually get a line through virtually 1 point. There are 2 points, clearly, but they're so close to each other that they look like they are really 1 point. And why is that? That is because h has been made to actually go to almost 0. Oh, remember what that means? It means that h is not 0. I still have 2 points. H is not 0, but it is so close to 0 that what we have here is no more a secant line. It actually turns out to be more like a tangent line. And we can actually, and that's the extraordinary thing, we can actually find its slope. We can find the slope of this line. Although now we really have only 1 point. Now in high school, if your teacher had asked you, find the equation of a line, but I'm only going to give you 1 point, you would have said, I don't have enough information, right? I need delta y over delta x, I need 2 points. But now I can actually find the equation of this line, and I only have 1 point. How am I going to do that? Well, it's the same slope as before. It's the same slope as before. Nothing has changed except one thing. What happened to the h? It became extremely close to 0. Now, that means that if I take the limit as h goes to 0 of this very expression, I am going to get the slope of the black line on the graph. Wow, that is quite extraordinary, huh? We have now a tool that allows us to find the slope of a line if we only have 1 point. That's like really, really fantastic. Now, this is so fantastic that it actually has a name. This later expression, is called, you've guessed it, what is it called? The derivative. Oh yeah. It's called the derivative. This is a word that you're going to hear very often in this course. Actually, I would say every lecture between now and the end. The derivative of f of x. Fantastic. So this guy here, I'm going to summarize this on the next whiteboard. This guy here is known as the derivative of f of x. Lovely. Okay, I'm just going to repeat this definition on the next one, but in the meantime I need the space in 2, 1, 0. Alright, all good. So I think it wouldn't hurt to see this in action in an example, so let's see if we can do this quickly. So definition, the derivative of f of x is limit as h goes to 0, fx plus h minus f of x all over h. A little bit of notation. The derivative of f is written, there are several ways to do that. We have f of x with a little apostrophe here. So it's not read f apostrophe. What is it read? Those of you who know, it's read f prime. We read this as f prime. Yeah, like Amazon Prime. That's it. Or y prime. Right? This is also read y prime. Or dy dx. This is read dy dx. Okay, in the next video, when I have a little more time, I'll tell you why there are two very different ways to express this, but not in this one. Okay, so let's see if we can actually do an example quickly on this. So I've used pretty much all this space. These whiteboards are so small, I will erase this and go for the example in 2, 1, 0. Okay, so example. Let us, example 1 in this section. Find the slope of the tangent line to the graph of, now we need some sort of an analytic function. Let us take something that actually looked like the blue curve that we had in the previous example. Let's call this y is equal to x squared plus 1 at the point x equal to 1. So basically what I'm finding here, just to give you like a quick idea of what I'm about to find, I had here y is equal to x squared plus 1. I'm going to take a point right here that I'm call 1. I'm going to take that point and go to the graph, get a point here, and calculate the slope of that very line. And how am I going to do that? Well, the slope, and I'm going to put here a subscript tg. That will mean slope of the tangent line. It's going to be the limit as h goes to 0, fx plus h minus fx over h. That's going to be the limit as h goes to 0. Now, let's replace. I know f of x, don't I? What's f of x? F of x is the same as y. Right? Now, what is f of x plus h? Well, we reviewed that in, I believe, review video numero 8, number 8. How do I get f of x plus h from this? Well, it's x plus h squared plus 1. Agreed? Okay, well, we have a limit, and I'd like to actually solve that limit. So I'm going to start with, you know, the good old beginning of the algebraic method, a good old cheat. Let me replace h by 0 here. X plus 0 is x squared plus 1 minus x squared minus 1 over 0. Well, look at that. An old friend of ours, or an old foe, depending on your perspective. Here's 0 over 0. What do we call 0 over 0? Yes, undetermined or indeterminate. Absolutely. So we have to remove the indetermination. Algebraically, what do you want to do here? Rationalize, factor, what? Expand? Yeah, expand and collect would be absolutely the way to go. So I'm going to expand this, and I'm going to get x squared plus 2xh plus h squared plus 1 minus x squared minus 1, watch your signs here, over h. What's this going to be? Limit as h goes to 0. Some cancellations, ladies and gents. Plentiful. Bye bye, Miss American Pie. Plus 1 minus 1. What am I left with? 2xh plus h squared. All right, I could rewrite this, but I could actually save some time by rewriting it where an h is factored. That is 2x plus h over h. Here comes another simplification. Ciao, ciao, bambina. See you later. This is going to be, what is this going to be? The limit as h goes to 0 of 2x plus h. Good. Now, cheat. algebra, cheat. I'm ready to put h0 in there. That is 2x plus 0. Well, we have here an expression called 2x. What is that? It's supposed to be the slope of the tangent line to this graph. The only thing we haven't considered yet is that this is the equation of the tangent line at that point, at x is equal to 1. So all we got to do to finish the problem is to let x equal to 1 in slope of the tangent line equal to x. And what is it that we get? We get that the slope of the tangent line is 2 times 1. Hey! So we did actually do something that we could not have been able to do in high school. We found the slope of a line given only 1 point. That's got to be progress. We'll do more examples. We'll deepen our knowledge and understanding of this in the next video. Sorry if this one was a little longer than the other ones, but we have to cover what we have to cover. I'll see you soon and you take care. Ciao.